Okay, so this is lecture 24, so second last lecture of our entire semester. So please wait. Okay, so this is lecture 24, the second last lecture of our semester, and let's go to the last content we have considered in our previous lecture. So in the previous lecture we have introduced many approximations to derive this expression for our drain current. So in order to derive this expression, we have introduced, for example, gradual channel approximation, which was quite a general one. So in that case, we neglect a certain component of electric field in our Poisson equation, so that was intentionally neglected. And after that, we have introduced also charge sheet approximation, so that was also related with another simplification. And by introducing these approximations, we were able to get this equation shown here. So point of this expression is now there is no longer any of no integration, so no integration any further. So when we know the surface potential at source end and surface potential at drain end, if we have two different boundary values for surface potentials, then it is enough to calculate this drain current. That was the main point of this expression. So previously, for example, if we have to consider Tau sa double integral, then in this case we must integrate the integration over our potential and also integration over our electron quasi-Fermi potential. This is corresponding to the actually the vertical direction integral, and also this dv integral is corresponding to the y integral, parallel or channel direction integral. So basically we must do this two-dimensional integral. However, previous that two-dimensional integral all eliminated, and now we have much more achievable task for our ID drain current calculation. So in the next slide, I would like to show you one concrete example of calculating this drain current using our equation 3.21. Please note that already this equation 3.21 contains approximations inside it. However, since those integrations are more or less reasonable, so we can go further in this case. So let's try to evaluate it together, so by step manner. So let's assume that relatively lowly doped p-type substrate 10 to the 17. So nowadays 10 to the 17 is just no doped actually, so this is quite a low dope. However, it is always a relative measure. So when we have 10 nanometer thick oxide, this is a really thick oxide. Nowadays, please note now our effective oxide thickness is even shorter than 1 nanometer in the most of state-of-the-art technology. So this is somewhat old technology. So just to show you the very basic of our ancestor technologies. and say that now gate voltage equal to 1.0 and flat band is minus 0.88 volt. Also, this flat band voltage itself shows us that this technology doesn't have quite high doping density. So if we have a high doping density, then this value, absolute value, goes to, for example, 1.0 or even higher number. But this relatively low value, 0.88, means that we are not having a highly doped substrate. Well, anyway, in this case, please consider a case of drain voltage which is equal to 0.1 volt. When you have this these numbers, then first of all you can understand we are now talking about very old technology. From what oxide thickness and doping density, you must understand these two. And another one is gate voltage equal to 1.0. If this technology is reasonable, then maybe threshold voltage would be positive number. However, it does not exceed 1.0. So what you can guess is okay, so maybe this number would be higher than threshold voltage, although we have not defined the threshold voltage exactly at this moment. However, you can understand at least we will have a certain inversion property. And when we have a 0.1 volt of a relatively small drain voltage, okay, then we will have a linear behavior of our transistor. So I think that this is a good example to show you the basic calculation method. First, we must calculate the source side surface potential. Then how can you calculate this source side surface potential? So we should calculate this number, so which is given by gate source voltage minus flat band voltage. So this is given because now we have a 1.0 as a given gate voltage, and flat band voltage is also given. So in order to satisfy this left hand side term 1.88, we have to find out the sufficient value or required value for our surface potential. Here we have this number. Well, if we have only this number, then it would be quite easy to calculate this equation. However, unfortunately, we have other parts containing also this surface potential. Here we have a surface potential, and here we have a surface potential, and of course here we have another surface potential. This is just a linear term, no problem at all. However, these two terms are arguments of our square root. So here we have square root, and here linear term and exponential term. So it is a highly nonlinear function. So it is not that easy for you to calculate this number, this solution phi sub s comma s directly, but anyway there can be multiple ways to calculate this number. So as a first simplest one, I would like to suggest a graphical solution. So please have a look at this graph. So this graph just shows so left hand side of our equation and right hand side of our equation. What is the left hand side? Left hand side term is just 1.88, so this is corresponding to nothing but just 1.88. So this is just a constant, so that's the reason why we have a horizontal line. And here the right hand side term is interpreted as an expression in terms of our surface potential. So now here we have phi sub s comma s as an independent variable, and we draw this right hand side term as a dependent variable. So this is corresponding to our right hand side term. So in order to get the solution, we must find out the condition where both of left hand side term and right hand side term are equal to each other. So when you have a look at this figure, then you can easily understand this condition is corresponding to the your condition for satisfying that previous equation, and by certain inspection, so you can find that roughly this number is corresponding to 0.006. But of course here we have also following digit, much longer digit, but approximately it would be okay. So now you can find that, okay, in this case you have 1.0 volt applied to your gate, and here you have your source side, and what we are doing right now is to find out the surface potential at source side. So in this case, by solving our equation, Poisson equation, together with our charge expressions, then now we found that this value is corresponding to, yes, phi s at this side equal to 1.006. And next task is, what is the next task? Now here we have another contact called as drain, and in this drain we have applied 0.1 volt additionally. So if we just treat this additional voltage as just additionally added to our surface potential, please try to guess what will be the value shown in this point. Okay, so please note that this additional 0.1 volt is directly related with increase of your electron quasi-Fermi potential. So in this source side, your electron quasi-Fermi potential would be just 0, and in this case your electron quasi-Fermi potential would be 0.1 volt. So it is expected there is a 0.1 volt difference, but this is not for surface potential, that is for quasi-Fermi potential. And actually phi sub SD should be recalculated. However, in this case maybe we can guess that so there will be just roughly 0.1 volt increase in this case. Why do we have such kind of a guess? How can we justify ourselves to make this one? So previously we have considered such quantity like dV over d phi s. Do you remember in our previous discussion for calculating certain expression for our ID expression? Then in the previous lecture we have found that actually this expression contains a certain leading factor 1 plus some quite complicated terms, and you know, this and that competing to each other. However, this term makes a certain contribution only when we have a quite low charge density. So do you remember? Only when we have a quite small inversion charge density, then this term make a relatively reasonable or meaningful contribution to our overall calculation. So simply speaking, now where are we now? We are now in highly above the threshold voltage, so we can expect that yes, maybe this dV over d phi can be quite close to just number 1. So by adding just 0.1 volt, we can expect this kind of just adding additional drain voltage to the drain side surface potential. Please try once again this calculation here, as shown here. The left hand side term is the same. However, when you have a look at this right hand side term with different unknown variable, it is no longer phi sub s comma s. Instead, it is a drain side term. And what is the difference between previous our equation, and our current equation? So the difference comes from this part. Now, this exponential term is related with electronic contribution to our MOS equation, and since we have electron quadriform potential corresponding to 0.1 volt, so now we have to modify our expression for electron by amount of 0.1 volt. However, please note that this part, the physical origin of this linear term inside the square root term, that is originated from just depletion charge, and depletion charge is not affected by this change of electron quadriform potential. Why? Because, you know, once again, in this situation, in this MOSFET, now think about this one. Here we have 0.1 volt, and this is the one for electron, and here we have electronic channel, and this channel is affected by this 0.1 volt. However, if we consider, for example, quantities like whole quadriform potential, the change of this electronic part does not play any role, but instead here we have grounded substrate or body. Then this body's quadriform potential directly affects the quadriform potential at this all over this system. So now we can say that, okay, whole quadriform potential is equal to 0 almost everywhere in this device. So that's the reason why when you come back to this case, depletion charge expression is not affected by our applied drain voltage. So now you can find that it looks quite similar to the previous expression, but you know, since now we have just minus 0.1 here, so onset of this rapid increase is delayed by amount of 0.1 volt. Please note that in this figure, actually this relatively moderate behavior is related to our other terms, and this sharp increase of our expression comes from electronic contribution. So simply it means that now this electronic contribution is delayed by our applied quadriform potential. So that's the reason why when you compare, when you make a comparison between, so can you do it together with me? So just please have a look at these two graphs. So these are two graphs, two blue curves just shows the right hand side for our source side expression, and the lower one is corresponding to the right hand side for our drain side expression. You can immediately understand that, okay, the point of this sharp increase is just shifted by amount of 0.1 volt, because this electronic contribution. So that's the reason why now we have a slightly shifted point. It's in here, and its number, if we just takes its number numerically, then that is corresponding to just 1.100 volt. So I did this calculation manually, and I found that this is the first one. So okay, then is this corresponding to your expectation? So if everything is perfect and just added to our drain side, then maybe you expect 1.106 volt as a phi s comma d drain side surface potential, but of course this was just an approximation, and we have a slight degradation compared with just one-to-one relationship. So now we have quite close but slight degraded value. Okay, so up to this point, wow, now we have calculated the surface potential at source side and surface potential at drain side. So by using these two numbers, then we can actually evaluate the numbers. So please try to do it. So you know Cox, you know gate voltage, flat band voltage, summer voltage, all of them are known, and actually you have to understand surface potential. But fortunately, by using the graphical methodology, so we were able to get a rough value of phi sub s. And please have a look at this second term, square of surface potential. Still, we have just Cox as its leading coefficient, so we know all of them, and epsilon, silicon, Q, and A, all of them are known to us, and power of 1.5, it is easily calculated by our calculation. And finally, we have another term. Well, everything can be calculated. So please try to evaluate this expression twice with source side surface potential and drain side surface potential, and by evaluating it, then you will get certain number. So having quite unconventional units. So Coulomb volt per square centimeter, but please note that this one is not the end of the story. What is missing? The missing quantity is corresponding to our electron effective mobility and the ratio between W and L. So this one does not give us any unit quantity, so this one is just a dimensionless quantity, number 1, 2, 3, whatever, and only remaining dimension, additional dimension, is that of effective mobility. What was the unit of this effective mobility? It was square centimeter times inverse of voltage and inverse of second. So when they are combined together, then you can immediately understand all of them, or most of them are gone. For example, volt and volt are cancel each other, and square centimeter and per square centimeter, they are eliminated, and remaining thing is just Coulomb per second. However, we have a name for this quantity, Coulomb per second, that is called as our ampere unit. So as expected, now we have ampere. So when you have these two numbers for source side and drain side, please make the difference and multiply certain number corresponding to effective mobility multiplied by W over L, and let's assume that for certain device it is corresponding to, for example, 500. So is this reasonable or not? Of course, it depends. If we have very wide device, wide length is or width is 10 times of our length, or width is 100 times over our length, then we can easily increase this number quite easily. However, think about another case like W over L is just close to number 2, so then this number 500 would be quite difficult to achieve for scaled device. If we are working with just moderate ones, so all the technologies, inversion charge, inversion carrier mobility, effective mobility can be, yes, 250, it can be achieved easily. But if we are working with highly scaled devices, then it would be difficult to get such kind of thing. Who decided this effective mobility? Actually, there are, in roughly speaking, there are two important contributors to this effective mobility. One is, of course, one is doping density. So if you have quite high doping density, then it directly affects your effective mobility. So this is quite a severe one. So please think about the case where you must use high NA, high p-type doping density. In this case, you must consider the degradation of your effective mobility. Well, then why we are forced to use this high doping density? So please think about the scenario where we must adopt high doping density. No, if we have scaled device, then the tendency is, if you just keep the doping density, then usually your threshold voltage reduced drastically. So, but there is a certain rule of thumb to maintain sufficient threshold voltage. Your threshold voltage is directly related to your VDD. What is the VDD? In a certain technology, the VDD is the maximum voltage you can apply to your device. Then the rule is between these two numbers, there is a 1/3 or a quarter ratio between this threshold voltage and VDD. So it means that if you wanted to make a certain technology, then actually from the beginning you have a certain specification for threshold voltage. Then let's say that you wanted to generate your new technology, then the tendency is, if you scale your geometric parameters, for example oxide thickness, then tendency is, if you don't spend any further caution on your device, then usually your threshold voltage drops too drastically. So you must introduce some ways to increase your threshold voltage, and the best way or direct way you can do is actually this one. If you increase your doping density, then you can further increase your threshold voltage. So the tendency was, when you introduce a new technology, always you introduce higher and higher doping concentration. So unfortunately, that is directly related with your lower and lower effective mobility, because the doping density is a direct contributor to your effective mobility. And as I told you before, there are two major contributors to this effective mobility. One was, as I told you, this doping density, substrate doping density. Another one is corresponding to so-called surface roughness. However, unfortunately, there is not many knobs for us to improve this quantity. Usually, more and less state-of-the-art devices or fab all over the world has certain universal behavior. So the quality of silicon and silicon dioxide interface controlled by human being. So this one is more or less a given restriction of our MOS system. Okay, so therefore, simply speaking, here I using the numbers like 500, but it really depends on your device. If you have, for example, wider device, then you can easily increase this number. And usually the minimum value of this W over L is corresponding to, for example, number 2 in VLSI devices. So the lower value of this leading coefficient, effective mobility multiplied WL, is given, but you can easily increase this coefficient just widening your technology. But you know, that is not that much clever way. If you have 10 times wider device, yes, you can conduct 10 times more current, good, but at the same time you are wasting you are consuming your silicon area 10 times. So please note that silicon area is directly related to the price of your chip. So silicon area is related with immediately to the cost. So please understand this one. So in order to make a fair comparison, usually we try to set the W as a reasonable value, for example, normalized to the width, then we make a certain comparison. Okay, so now we were able to calculate the ID value corresponding to this specific bias point, like gate voltage equal to 1.0 and drain voltage equal to 0.1 volt. We were able to calculate this number. Okay, that was one point in our IV characteristics. So let's do it repeatedly by changing our gate voltage, drain voltage, and try to calculate it. So in this case, in this slide, I'm just drawing the input characteristics of our model device, and here I introduce a low VDS of 0.1 volt. Of course, we can repeat this job with higher values like 2 volt or 2.5 volt, so but you can do it. So please increase your gate voltage while keeping, means that this is fixed VDS. Our drain voltage is kept as just 0.1 volt, and just to ramp up our gate voltage up to 2.5 volt. Then how does it look like? So here in the left hand side, here we have linear scale curve, and this right hand side we have semi logarithmic curve. So please always you must draw these two curves at the same time. So please have a look at this one. So simply speaking, this device has just turned off behavior in quite low values of our gate voltage, and beyond that gate voltage, then after that it just behave like a linear something. So if we introduce gate voltage linearly, then our conductance is increased also linearly. But please note that this is nothing related with just a normal resistor. There is a severe difference between normal resistor and our transistor. So think about our normal resistor. Usually when you apply certain voltage and after that you apply additional 0.1 volt, then what you can expect is now we have more current is conducting. So in this case, but the case we are considering in this case is now the voltage at this drain contact is fixed as 0.1 volt, and now we just change our VGS value to VGS plus 0.1 volt. Additional voltage is applied to the gate terminal, and the additional current flowing not through the gate terminal but additional voltage through this drain terminal. So there is separation between the voltage applied contact and current monitored contact. So this is quite important. They are separated. So signals is applied to this input terminal called as gate, and the response of our device is taken at another contact called as output terminal or drain contact. So this separation is quite important. In the case of our resistor, so when you apply this additional voltage to your second contact, then also that response is occurring at the same contact. Your second contact, second terminal current is increased or decreased, so input and output cannot be separated in this two terminal device. However, if we introduce a three terminal device, one of them is used as a voltage reference, and one of them is used as input terminal, and the remaining, the third one, is used as the output one. So that is critical difference between just two terminal device and three terminal device. You will find so many different examples when you really consider real world problem. So for example, nowadays there are many different alternative ways to realize certain kind of memory devices, or sometimes even neuromorphic chips. And in this case, there are some competing two approaches. One approach is using just a resistive component for your memory element, or sometimes they are trying to introduce transistor structure into as your memory devices. Then of course transistor type is more complicated because it should support additional one more terminals. However, since input and output are separated, then you have more possibilities or more ways, additional ways to control the behavior of your memory element. So you will see in your actual study or research this important difference. But anyway, let's come back to this one. So now here we have a clear behavior, just turned off behavior and linearly increasing conductivity of a channel. So there is a certain voltage where our transistor change its behavior. Below certain voltage, for example, it is not responding to the change of gate voltage. However, beyond this voltage, now our transistor is really linearly reacting to this applied voltage. So usually this voltage, so linearly extrapolated from our linear ID versus VGS characteristic, this is regarded as a good estimator for our threshold voltage. So simply speaking, we are saying in this way, if our gate source voltage is higher than threshold voltage, then we can collect our inversion charge corresponding to C ox times this way. And of course here we have a minus sign because Qi in this case regarded as electronic contribution to our net charge, silicon charge. So yes, so we have this kind of a quite good approximation, and this value is just estimated from this expression. Quite good. And please have a look at this log scale, semi-logarithmic scale. Here we have certain exponential increase of drain current with respect to the gate voltage. So of course, in this case, actually we have a quite small amount of current. So actually we wanted to have completely no current in this region. However, unfortunately, our current does not vanish at all, and now we have a certain amount of current. Certainly, this current is not desirable one, so we wanted to reduce it, but it's not possible. And this one is sub-threshold current. So the reason why we call it as a sub-threshold current, because here we have threshold voltage, and the voltage below this threshold voltage is called as sub-threshold. So it means that the gate voltage lower than threshold voltage. In this case, we can get certain current conduction that is called as sub-threshold current. Okay, so it shows quite a typical exponential behavior, and this exponential behavior is very important. If you have, let's assume that if you have this exponential behavior and say that you have much degraded slope for your another device, then please try to make a comparison between your two devices, blue one and red one. Which one is good for your application? So although they share the same behavior beyond threshold voltage, if we have two different behaviors of our sub-threshold voltage, then it means that if we go to lower and lower gate voltage, then this blue curve will give us much higher threshold voltage and sub-threshold current, and this red curve will show or give us much smaller value for our sub-threshold current. So which one is desirable? Of course, we wanted to have this lower one, so that's the reason why this sub-threshold behavior should be quite steep. This one is much better than this one, and of course this one is better than this one. Okay, so I hope that everybody in this room can understand this slope related ones. And then why don't we have just a vertical line? Why don't we try to make such kind of a vertical device? I mean that if we can make a certain device, for example, this is gate source voltage and drain current, and there is something, so, and let's say that there is a certain voltage below this voltage. Let's say that we have just a vertical drop of our IV characteristics. After that, the current just goes to its noisy level. Then if we can make such kind of devices, then we will be very happy, because yes, so below certain gate voltage, for example, let's call it as just once again threshold voltage, and below it the current, sub-threshold current is minimized. It means that we can reduce the standby power of our electronic system drastically. So that was a long desire for many engineers, and they have tried many ways to achieve this kind of behavior. Unfortunately, in the case of our conventional MOSFET we are now currently talking about, it is not achievable. So as we'll see later, maybe in the last lecture, lecture 25, there is a well-defined maximum slope we can achieve. So let me just throw it here. For example, let's say that this is the given maximum slope we can achieve. Then instead there has been two different approaches. One approach was, okay, that is the maximum one, then let's make it. So the current situation is our state-of-the-art device really achieving this maximum slope. Wow, they did it. So we have now quite ideal subthreshold slope, and beyond that, that cannot be done in our conventional transistor structure. So instead they have introduced many ways, so I can name them, many of them, but unfortunately right now there is a clear successful application of this kind of some innovative approach to solve this problem. But please note that this is really a long desire of our electronic engineering, electronic device society. And another way, we have another way to improve this slope. This slope is really related with temperature. Wow. So it means that if you cool down your system, then actually you can achieve steeper behavior. So there are strong tendencies for certain engineers, wow, instead of operating our system at room temperature or above room temperature, why don't you just make it cool? Then we can have a much better subthreshold slope, and it is good for saving the power consumption. But there is hidden cost. Then how can you make a overall cooling for that your computing environment? So in order to reduce that temperature, one possibility is build your data center not in this Korea or California, but build it on the close to North Pole. Or other way is just dump our data center into the sea, deep into the sea, because it has a lower temperature. Or sometimes they are trying to send it to space, then of course space we have a completely low temperature. So good for, yes, all of these attempts are good in some sense, but there are always some hidden cost. What is the maintenance? If you just dump your data center deep into the sea and something happens, oh, we must fix it. Then send our engineer into deep sea, or just we can. Okay, so there are many different practical problems, but please understand this one. This behavior is one of the most important topics in our electronic devices. So sometimes we are having certain tendency to always talk about this quantity. This is corresponding to the maximum current, the current we can conduct when we apply high enough voltages. But in the realistic case, if you wanted to make a real chip out of this technology, then more important one is sometimes to this level, where when your system is in its sleep mode, how much power is consumed by just turning it on. So that is related to this number. Okay, so anyway, Up to now, I have just briefly discussed about input characteristics, and now let's go to the output characteristic. This output characteristics is simply nothing but just ID versus VDS at various VGS values. So here, for example, by changing our VGS from 2.5 volt down to 1.0 volt, you can see the change of our curves. So it is certain that if you apply higher gate voltage, then since we can collect a lot more electrons, so the current will increase, and if we reduce it, then we have relatively low values of current conduction. That is quite easy to understand, and also you can clearly identify certain behavior shown here and there. In this case, you can identify a parabola-like behavior of your curve, and after that, beyond a certain point, then it is just showing a constant level called as a saturation current. So below it, it can be approximated as a parabola, and beyond it, this is just a horizontal line. Of course, everybody in this room now understand this is not a general behavior of a MOSFET. We have this kind of behavior, quite an ideal behavior, only because currently we are talking about a long channel device. So in the last lecture, we will talk about briefly the behavior when we have not long enough channel. In this case, many different effects can happen, but if we consider long channel, then we have this kind of behavior. So please note that what is long or what is short really depends on the technology. So for example, if we have, for example, 3 nanotechnology for certain, so if we say, for example, 90 nanometer technology, then 2 hours, then 1 micrometer channel, L equal to 1 micrometer, that can be clearly regarded as a long channel device. However, previously we had a technology whose minimum channel length was just 0.5 micrometer or 0.25 micrometer, half micron or a quarter micron devices. To them, actually this 1 micrometer, but their 1 micrometer device does not show long channel behavior because it's just twice longer than minimum achievable or minimum drawn gate length, or 4 times only. So please understand the concept of a long or short is really depends on your technology. Okay, so then let's move to this one. Okay, so up to now, today I have spent more than 15 minutes to discuss about how can you calculate surface potentials at 2 different sides, source side and drain side. Out of them, how can we calculate the IV characteristics and just describe their behavior, input characteristics and output characteristics. So it sounds good, but point is, even in this case, what we must do is we have to calculate surface potential at source and surface potential at drain. This was related with the calculation of these 2 numbers, and that was also related with solving 2 nonlinear equations. Engineers hate this procedure, so they really wanted to make even further approximation. So please have a look at this one. So right now our goal is to calculate phi s, comma s, phi s, comma D. So why don't we just say this way? At source side we have an first of all we must restrict ourselves to this one. So now we just give up to consider sub-threshold region. We assume that already our gate source voltage is higher than threshold voltage. Okay, now we have inversion. When we have inversion, then from our previous discussion, the surface potential is more or less roughly fixed to this 2 times phi b. That was surface potential pinning. So surface potential pin. So, but please remember that when we say that this is fixed to 2 times phi b, that was quite low. I mean that if this number is, for example, 0.8, however, our actual surface potential can be increased up to 0.9 or 1.0 when we apply, for example, 2 volt of gate voltage into our MOS system. So when we say this value is pinned, then we have to understand in this way. Compared with the increase of gate source voltage, additional gate source voltage, compared with this large variation, actually change of our surface potential can be negligible compared with this huge difference of gate voltage. For example, gate voltage changed from 1.0 to 2.0. We apply 1 volt. However, the increase of our surface potential is not 1 volt, but it is just, for example, 0.1 volt. So that was the meaning of this surface potential pinning. But in this approximation, we will just believe this surface potential as a good approximation. Wow! So source side surface potential is regarded as just fixed to this number. In reality, what is it? In reality, we have certain additional value. So our phi s, s would be a little bit higher than this number, but we just say this number. And also we assume that the value surface potential at drain side is just given by adding our VDS value. So you have already seen its validity, because previously we have just applied 0.1 volt and the actual phi s, d was increased by 0.094 volts something. So it can be a good approximation. So please note that already these two expressions are not that much accurate. So we don't like it. But anyway, once we adopt this one, then we can make quite much simplification for our ID expression. So when you just introduce this one, so I will skip the derivation procedure, but it is really easy. Then you can now have another expression for ID. Previously, when we consider equation 3.21, at least we had to calculate phi sub s, s and phi s, d. However, right now, in this case, we don't have anything. Just once we know VDS, then of course VGS, we can calculate this number. What is the magic? How can you make such kind of a great further simplification? the simplification was by introducing a relatively crude approximation for these two boundary values. So we don't have to solve it any longer and just to insert these numbers into our expressions. So now we have this expression. So what you can expect is, well, it is quite much simplified. However, its accuracy can be degraded by our introduced additional expressions. Well, but anyway, let's have a look at this one. Okay, so from this expression we can make certain linear approximation. So here we have VDS, and in the next slide we say that VDS is really close to 0. It means that it is not 1.0 volt. Instead, it is just 0.1 volt or 0.01 volt. It's just a few millivolt. So we will assume this kind of smallness of VDS. Then, if we have this kind of small VDS, then here we have second order term, VDS multiplied by VDS. Then this second order term can be well removed, and here we have a power of this VDS related term, but we can introduce so Taylor expansion for this one. Well, how can you do that? So if you have 2 times 5e and VDS and 1.5, that can be Taylor expanded with just insert VDS equal to 0, then you will have 5e and it's 1.5. And after that, what we can have is now linear term. And what is the linear coefficient for this one? That will be 1.5 to 5e and VDS and 0.5. That is evaluated at VDS equal to 0. So this term goes away. So remaining term is just 1.5 and 2.5e. It's a 0. Square root and VDS. That will be the linear term for our this power of 1.5. So by applying this expression, this is nothing but just a Taylor expansion, neglecting second order term, and just to expand our nonlinear term up to only linear term. Then as a result of this expansion, now we have quite a simple form. When we have low VDS, when VDS is quite close to just number 0, then we will have this behavior. So simply speaking, so VGS minus VT, this quantity, usually this quantity is called as gate over drive voltage. So depending on the gate overdrive voltage, our channel conductance is increasing. And here we have a certain quantity defined as VT, and this VT is called as a threshold voltage, and it can be written as this form. The physical meaning of this VT is simply the gate voltage when surface potential reaches at 2 times 5e. So when we make a surface inversion, this point is regarded, this gate voltage is regarded as threshold voltage. But please note that this expression is already obtained from several approximations, and what was critical was this expression. At source side, our surface potential is fixed to 2 times phi b, but in reality actually we have an additional one, because surface potential pinning is not absolute one, so it is a relative meaning. So when you just evaluate the threshold voltage VT following our numerical definition shown here, equation 3.24, you just get the numbers corresponding to 0.1 volt. And please make a comparison between your numerical value 0.1, theoretical value 0.1, and your linearly extrapolated values shown here. So where can you find 0.1? Your 0.1 can be found at this point. And from the actual calculation, now you have the number quite close to 0.3. So roughly speaking, there exists 0.2 volt difference between theoretical value of threshold voltage and actual numerical value of threshold voltage. What is the difference? So main difference comes from, once again, our approximation for surface potential. Since we have assumed that surface potential is fixed to 2 times phi b, that is the main cause of this kind of discrepancy. So if we just use this numerical value calculated, this 0.11 volt as a threshold voltage, then when we draw IB characteristics, output characteristics for example, then it looks like this. Here I used VT equal to 0.11 volt, and you can see that at a given gate voltage, so this is corresponding to 2.5 volt over our gate voltage, and at the same gate voltage we have 2.5 volt. Some certain discrepancy is observed. Why? Because our threshold voltage itself is shifted by roughly 0.2 volt, so that's the reason why we don't have perfect agreement. Then please have a look at the right hand side. This one, how do we get such a good agreement? Here there is no no theoretical background. I just shift my threshold voltage by amount of 0.2 volt in this expression in our tower equation 3.23. I intentionally changed the threshold voltage by amount of 0.2 volt just to match our observed behavior, and now you can see that. How does it look like? The agreement looks quite much better than our previous one. So as you can see, we have introduced many approximations, and by depending on the accuracy or validity of our introduced approximations, so the result can be significantly changed. Then maybe you can ask me this question. Well, I just have observed that already this expression, so the newest one, is not that suitable to describe our IV characteristics. So I will not use this equation any further. So this is not our philosophy. Our philosophy is to derive the expression for ID, which can be actually used in our practical purpose. So actually these comparison should be interpreted as this one. Although we have to adjust our threshold voltage by 0.2 volt, once we adjust a certain parameter called as threshold voltage to the more reliable data, then we can well reproduce the result of a more complicated calculation. So are you with me? This is the basic approach or philosophy of device engineers. Okay, we are not trying to find the most rigorous expression. The most rigorous expression is already known to us. What was it? Tau-sa double integral was the most rigorous one within the gradual channel approximation. But if we have to evaluate this Tau-sa double integral every time, then it will take quite a long time and quite tedious. But using this amazingly simple expression, what is the amazingly simple expression? So as shown here, this equation 3.22, there is no need to evaluate the solution of a nonlinear equation, and it is just inserting your numbers, then you can immediately calculate this one. And although your computational burden is reduced drastically, but the cost you must pay is, well, I have to now calibrate my parameters a little bit, so it is quite an attractive option to the device engineers. Please understand the situation. The main message of this lesson is, okay, at the beginning, so we can do it quite rigorously. However, as a device engineer, we can consider many different levels of complication, and sometimes people prefer to have the simplest one with certain calibration. So that is the thing we have studied in today's lecture. Okay, so we have only one remaining lecture. In the last lecture, we will quickly cover this parabolic prism and move to certain sub-threshold current and shorten and that will end our entire semester. Thank you.